In this example, or this video, I'm going to work through numerous examples of electric force calculations using Coulomb's law. In example 1, I have two charges, and the distance between them is going to go and triple. So they start here. So this is charge 1, this is charge 2, and if we triple the distance, it goes from here to, let's see, 1. So now it is that far away. So originally, the force between my two charges was kq1, q2 divided by r squared. And my new force is kq1, q2 divided by 3r squared. So removing the parentheses, kq1, q2 divided by 9r squared, and I look and I see, oops, well, we'll just put a new tail on the 9. That this combination, kq1, q2 divided by r squared, is just my original force. So that's my original force with a factor of 9 left in the bottom. So when I triple the distance, I have decreased the force by a factor of 9. This is a property of an inverse square law. And this question hopefully looks very similar to what we saw when we were working with the law of universal gravitation. Let's do one more example like this. In this case, we're decreasing to a fifth. So here is charge 1, here is charge 2. They're originally separated by r, and now I have to try to figure out how to divide this in 5. Let's see, 1, 2, 3, 4. That does it. So new r means it is roughly here. So it's 1/5 our original distance. Our original force is kq1, q2 divided by r squared. Our new force is kq1, q2 divided by 1/5 r, that whole thing squared. So that's kq1, q2 divided by 1/25 times r squared. And I see I can group again. So that is our original force divided by 1/25, or 25 times the original force. In example 3, I have a 1 Coulomb charge and I have another charge, but I don't know how big it is, so I'm going to label it with a question mark. I'm told the distance between them is 2 meters. And that the force has a value of 500 newtons. And I want to know the unknown charge. So I use Coulomb's law. The force is 500 newtons, so I'm going to plug that in. K is a constant with a value of 9 times 10 to the 9th. Q1 could be our 1 Coulomb charge. Q2 is the other one we don't know. And it doesn't matter which one you call Q1 and Q2 because they're multiplied. And then our distance is 2 meters, and we square that. So doing some simplification, we got 500 equals 9 times 10 to the 9th times 1 divided by 4, which is 2.25 times 10 to the 9th times our charge, Q2. So Q2 is going to equal 500 divided by that big number. I don't know where that just came from. 2.22 times 10 to the -7th coulombs. So it doesn't take a very big charge to get a fairly substantial force. In example 4, we have a 1 coulomb charge. We have a 2 coulomb charge. We want to know how far apart they are. So that would be R. And we're told that the force is 3 newtons. Again, this is an example of Coulomb's law, so let's start by writing it down. K is 9 times 10 to the 9th. One charge has a value of 1 coulomb. The second charge has a value of 2 coulombs. And R is what I want to know, and I'm told the force is 3 newtons. Okay, so that is 3 equals 18 times 10 to the 9th divided by R squared, or R squared equals, I believe that is 6. Yep, 6 times 10 to the 9th. Right now our units are meters squared, so R is going to be the square root of that. They are 7.7 times 10 to the 4th meters apart. So we had small charges, actually those are actually fairly large charges, separated by 77 kilometers, so really, really far away, gives us a 3 Newton force. So when I say that the electric force is actually a fairly big force, you can see what I'm looking at here now. In our last example, we are going to combine ideas from this week with last week. We have an electron. So here it is. I'll label it with an E so we know it's an electron. And we have a 2 coulomb charge, and they are 3 meters apart. I want to know what is the electron's acceleration right upon the time of release. Okay. Because as it moves closer, the force will change, which means the acceleration will change. But at the time of release, we can find it given this information. We know that the net force equals the mass times the acceleration. That's Newton's second law. We learned it last week. And if we look at the electron's free body diagram, ignoring everything else, the only force on it is the electric force. So the electric force is what's causing our net force. So that's K times the charge of the electron times the 2 coulomb charge divided by R squared equals MA. So in order to do this, we need to know what the charge of the electron is and what the mass of the electron is. We know the charge of the electron, hopefully. It's 1.6 times 10 to the minus 19 coulombs. I'm ignoring the minus sign because that's just telling me something about direction, and I know that my electron will be attracted to the plus 2 coulomb charge because opposites attract. If you look in the cover of your book or ask Dr. Google, you are told the mass of the electron is 9.11 times 10 to the minus 31 kilograms. So now I have all the information I need to find the acceleration. Plugging in numbers, I get K is a constant at 9 times 10 to the 9th. The electron's charge is 1.6 times 10 to the minus 19 coulombs. Our other charge is 2 coulombs. Our distance, we are told, is 3 meters. The mass is 9.11 times 10 to the minus 31 kilograms. And the acceleration is what I want to know. So to find this, the first thing I need to do is multiply everything on the left side of my equation here together, 9 times 10 to the 9th, times 1.6 times 10 to the minus, 19, times 2 divided by 3 squared. So that all works out to be 3.2 times 10 to the minus 10th. That equals 9.11 times 10 to the minus 31 times the acceleration. So now to find the acceleration, I just got to take my 3.2 times 10 to the minus 10 and divide by 9.11 times 10 to the minus 31. 3.5 times 10 to the 20th meters per second squared. So it is going to accelerate. It is going to accelerate very, very, very quickly. And remember, as the electron moves towards the 2 coulomb charge, the force gets bigger, which means the acceleration will get bigger as well.